Exercise 13. Theory of small numbers algorithm. When faced with small samples, an algorithm using alternate distributions such as the alternate Pert may be able to elicit a somehow better distribution than just a simple Pert. We consider a small sample starting on 3 data points and as much as 20 to 25 data points. With n being your sample size, calculate 2 percentiles, 1 divided by n plus 1, as a minimum sample, and 1 minus 1 divided by n plus 1, as a maximum sample, and a calculated median. This algorithm is based on the idea that, by increasing the number of samples, the remaining tails of the elicited distribution become narrower beyond those points specified by the smallest and the largest numbers of the sample. Simply add 1 to the sample number in order to determine the number of intervals at which the distribution is segmented. In other words, if the sample were to be of 4 data points, then we would create 5 equal intervals each containing 20% of the probability distribution. Therefore, the smallest of the 4 numbers would be the 20th percentile and the largest would be the 80th percentile. In a larger sample case with 19 points available, then the smallest number would correspond to the 5th percentile, given the 20 equally distributed intervals, and the largest number would correspond to the 95th percentile. By increasing the sample size, the remaining tails of the implied distribution become more extreme every time. Consider that not always an alternate Pert distribution, which is the one that we will use for this exercise, will necessarily converge given the calculated parameters. 1. On cell B108, insert the formula to calculate the mean of the small sample, equals average range. 2. On cell B109, insert a formula to calculate the minimum value of the small sample, equals min range. This is the actual number that will be used as the lower percentile value. 3. On cell B110, insert a formula to calculate the maximum value of the small sample, equals max range. This is the actual number that will be used as the upper percentile value. 4. On cell B111, insert a formula to calculate the range of the small sample, equals B110 minus B109. 5. On cell B112, insert a formula with a median Excel function to calculate the median or 50th percentile of the small sample, equals median range. 6. On cell B113, insert a formula to calculate the size n of the small sample, equals count range. 7. Calculate the lower percentile on cell B114 inserting the formula, equals 1 divided by n plus 1. 8. Calculate the upper percentile on cell B115 inserting the formula, equals 1 minus B114. Here comes the key formula that integrates all the previously calculated information on an alternate Pert distribution. Alternate parameters allow you to specify values for percentiles of an input distribution instead of the traditional arguments used. The percentiles to be entered are specified by the alternate distribution parameters options, displayed when alternate parameters is selected. 9. Click on the Define Distribution icon and select a Pert out of the palette. Even though @risk provides a whole tab for creating alternate parameter distributions, you can always start from a standard Pert and customize it with differently specified percentile parameters. The following general Pert distribution appears. 10. Click on the Parameters Standard Setting drop-down button and check on Alternate Parameters to show the following window. At this point, @risk can change the traditional standard parameters of a Pert, for example, the minimum, most likely and maximum parameters to alternate ones. By predefined settings, 3 percentiles may be alternatively entered with standard values of 5%, 50%, the median, and 95%. These parameters can be changed and, later on, we will change them to represent the dynamic nature of this algorithm. Just click OK without changing the percentile values. @risk will now show a distribution window ready to insert values to these 3 percentile parameters. 11. Using the Assign Excel References as Arguments button, click to retrieve the 3 parameters on this window. The first parameter corresponds to cell B109, where the minimum sampled value has been placed. The second parameter effectively corresponds to the calculated median on cell B112. The third parameter corresponds to cell B110, where the maximum sampled value has been calculated. Do not mind at this point that the corresponding minimum and maximum values do not necessarily match the 5th and 95th percentiles respectively. We will soon modify this on top of the formula being created. 12. Click on the upper right-hand corner of this window to return to @risk's newly created alternate parameter Pert distribution function, which will now look like this. 13. Close this window by clicking OK and edit the newly created formula. Two parameters now have to be manually changed on this function to correspond to the dynamic lower and upper percentiles. 14. Change the 5% on the formula for the lower percentile on B114. 15. Change the 95% on the formula for the upper percentile on B115. At this point, the formula should look like this. Equals risk Pert alt B114, B109, 50%, B112, B115, B110. It has now become dynamic. Take a look at the chart once this formula has been completed. 16. Now, add a couple of data points on the sampled range. For example, respectively, 74 and 47 on the 12th and 13th positions of the sample range, and observe how the lower and upper percentiles on cells B114 and B115 change, as well as the other calculated statistics. If at this point, you were to open with the At Risk Define Distribution button, cell B108, the distribution would look like this.